Hi, my name is Tristan Debleger. I've had the pleasure to work with the Center for Research in Computer Vision at the University of Central Florida, and I'm here to present our work, a video transformer-based framework for event camera-based action recognition. Action recognition is a key part of robotics, as it allows one to truly understand what's happening in front of them. While regular cameras capture brightness, color, etc., event cameras only capture movements. They have very low latency and are adaptable to very fast-paced environments. While there are existing methods for action recognition on event data, there are limitations. The first one is those methods tend to use data coverage architectures, which are not going to work for different data sets. The second one is those architectures do not leverage the advancements in RGB action recognition that we have seen in the recent years. Our main contributions is the use of the video transformer network, event-specific augmentations, event contrastive loss, and state-of-the-art results on NFA kitchens. Event cameras return us a series of events which all have a X and Y position as well as a negative or positive polarity. The latest feature here is the time, but because of the low latency of the cameras, we have a very wide range of time, and therefore we're going to stack all the events from a time window into a frame. And the results look like this. So this is frame 1, frame 2, and the last frame. Each frame captures a temporal span, and we're going to use the video transformer network, which is known to be efficient for spatial and temporal operations. Once we have our complete image sequence, we're going to pass in each image into an image encoder to extract the spatial features. We're then going to pass those into a temporal encoder that's going to study the temporal relations between each frame and pass that into a classification head, then into our cross entropy loss. Here we're going to add, right after the image encoders, a event contrastive loss, which we'll get back to. Let's get into event augmentations. Once we have a clip, we can decide to augment it by removing some of the events. Back to time windows, we can choose to vary its size to create different versions of the same clip. So a larger time window will equal to a lot of events per frame, and a smaller time window will equal to a lot less events per frame while showing the same clip. This is where we get into event contrastive loss. So here I have two augmented versions of the same clip, and I have frames 1 through 3. I'm going to extract the features of the first frame, and I will make sure that it matches as closely as possible as the features from the first frame of the other version. And once I have that, I'm going to make sure that it also looks as different as possible from all the wrong frames. We then jump into our second dataset, which is actually an emulated event dataset, as it is a post-processed version of the Epic Kitchens dataset. For the results, we obtain a 74.9% accuracy, which is an almost 10% increase on the previous state-of-the-art method. And we try that on different kitchen as well, and we obtain state-of-the-art again, beating all the other methods that often use a combination of events with other data type. Because our model uses a single modality of data, we obtain a much faster processing time than other methods do while having state-of-the-art results. Okay, let's get into our data sets. We have a first one that's recorded from a real event camera. We obtain very competitive scores with an accuracy of 97.9%. Back to our DVS dataset, we measure how each part of our method impacts the results we're getting. So if we remove the contrastive loss, we lose 2% accuracy, and if on top of that we remove the event augmentations, we lose 5% in accuracy. We compare them to different models. If we don't use a transformer, we get an 84%. If we use another transformer, we get a 95%, and using a method gets 97% while using a lot less parameters. To summarize, we propose a method that works both for real and emulated event datasets. We introduced event contrastive loss and event augmentations, and we obtained state-of-the-art results on Epic Kitchens with a very good accuracy versus speed trade-off. And along the way, we get very competitive on results on DVS while not using a dedicated architecture. Here are our references. Thank you.